So it's great to be here in Chile and to be part of this amazing congress and ideology of how we can work together to hopefully make changes that can benefit humanity. And today what I want to talk about is adding bacteriophages to that dialogue. So a bacteriophage is a virus. We can see some here escaping from a bacterial cell. So they're viruses that specifically infect, target, and kill bacteria. And this is really useful at the moment because we have many, many bacterial diseases that are resistant to antibiotics. So there are many diseases now that were normal infections that previously you would have an antibiotic, like a chest infection, for example, and now they're not working, so we need something else to be able to treat humans and also to be able to treat animals. So today what I want to do is talk about a little bit what bacteriophages are and the types of work that we need to do to be able to translate them into useful products. So I thought I'd start with showing you a case of where bacteriophages were really useful. This was a case in London. There was a young girl. She had cystic fibrosis. Her infection was resistant to all of the antibiotics that the doctors had. So they had to, she was just given a few days left to live. But luckily, her mother had heard of bacteriophages, so they contacted this man, Graham Hatfield from Pittsburgh, and he helped her find some phages. They treated her, and she lived for several years. So this was very nice for her, but actually being able to access the technology of bacteriophages is not normal. It's not routine. So what we're trying to do here at the university in Leicester is trying to find bacteriophages and do the work that's necessary to be able to help with that translation. So this is just to show you from Santiago to Leicester. And what we're really trying to do is find phages both for human and animal infection to really address these challenges in medicine and biotechnology. So what are the main challenges, or what do we want as humans? Well, two of the main things are having good healthcare. And this is what's being threatened with antimicrobial resistance. So we can see in this chart, we can see that this is the number of deaths per year in millions at the moment. And you can see antimicrobial resistant infections at the moment. This section here is sitting around 2 million people are dying every year. But if we don't do anything, by 2050 we'll have more than 10 million people dying every year. So it's similar to the number of people that are dying of cancer. So we have a real need to find something like bacteriophages and make them work. Now, the other interesting thing, of course, we need food. We need sustainable food. The human population continues to expand, the demographic changes, but we need food. And the link really between phages and linking food and human health is that a large proportion of our antibiotics that are made are used in animal production. So the food that we consume, the animals have been exposed to antibiotics, and that's pushed antibiotic resistance within that context, which means that when we have just do normal things like eat our food, we can be exposed to bacteria that have already developed resistance. Now, they can also, these bacteria, we're connected to our environment, so there's a connection between animals and the environment, humans and the environment. So we can see within this whole sort of One Health context, we're breeding bacterial that are resistant, we're consuming them. So we need to do something about that. So we can potentially use phages to treat the animals or to treat the humans or even to improve the environment. So we know that the antibiotics are not working. We know that the resistance rates are getting higher and higher, and bacteria are becoming increasingly difficult to treat. But really, phages, their discovery predates antibiotics, and there's so many of them. They're just naturally there. So if we look here, this is looking at some seawater under a fluorescent microscope, and we can see all of the large particles are bacteria, and all the tiny ones are phages. So for every bacteria in existence, there are between 10 and 100 phages that exist that can kill that bacteria. So what we're trying to do is find those ones and bring them into bring them into isolation so we can then develop them. So I'm going to show you a very short clip just to explain how bacteriophages work. Phages are essentially bacterial killing machines, and they're absolutely everywhere. So for example, in this pot, there are about 100 million bacteriophages. Now they are incredibly specific. So for example, Pasteurella, the bacteria we're interested in, there will just be a few phages that can infect it. And what they'll do, they'll attach to the surface, they'll inject their DNA, they'll turn that Pasteurella into a phage-making machine, and hundreds of phages will be released into the environment. So because phages are such useful bacterial killers, they cannot be used to remove disease. So over the last decade, we've been using them to remove diseases both from swine and poultry. And now what we want to do is introduce them into the aquaculture industry, where they could again be very useful because you have a self-replicating medicine at the site of infection that doesn't kill the rest of the useful bacteria. Okay, so that's why they're so useful. So how do we go from this, all these abundant bacteriophages, into this, having products within our healthcare systems, within England, within Chile? So the panel in the middle is showing how they're used in Georgia. So Georgian biologists at the Institute, the Eliava, they make these really interesting mixtures. We'll have maybe 50 different phages in there, because the bacteriophages are very specific, so you need a lot of different types if you're going to make a general preparation. So this is the way that they commonly use phages within this healthcare system, but we need to figure out within individual healthcare systems what is the best route to translation. And the same with animal products. How do we make products for swine and poultry, fish farming, and even, of course, growing crops? Crops are very susceptible to bacterial infection. How can we support our crops? Well, the three types of research that we do are, we're doing the discovery. So actually, it's not always easy to find the phages for all of the bacteria. So we have a big discovery program. So this is what we're doing in Leicester and other phage biologists around the world. You find them, and then you can characterize their genomes and establish banks. Then you have to check they behave as you expect in a model environment, and then talk about that with the end users to be able to make a very useful product. So let me just show you a few more little bit of information on these different aspects. So this is illustrating the discovery. And can you see the little tiny holes in the square plate? This is where we've actually found new phages. And what's different now from previously is we can go quite quickly to sequencing the genomes of these phages to get very useful information. So we spent a lot of time doing that to establish the banks. Then, in terms of the research, there's no point just in having a bacteriophage that works well in a flask or in a laboratory. We need to check. This is two examples of different food products. So showing how we would show how they work to make a product for shellfish to prolong the life of them, and also to stop potatoes rotting. So we need to check that the phages will work when they're given to, for example, the potato. And then clearly, after we've done that research, we need to talk to the end users. So in a medical context, that's talking to the doctors, talking to companies, talking to regulators. So what is happening within this field of phage biology is we're doing a lot of that very key science, followed by that necessary working out how they work, and then engaging with those end users to make actually a useful and effective product. So now I'm going to take you to a sort of day in the life, well, probably more like a year in the life of a phage biologist, to show you the types of work that we do. So this is actually finding the viruses in the first place. So can you see those holes? That's where we know we've got something. And this is to show you the sampling is not very high tech. We just grab some water very often that we think phages might be in the natural environment, and then we can look for the viruses. This is always a very nice moment here where we finally get to look at them under the electron microscope, so we convince ourselves that those holes actually are these organisms. So what we do when we find that water, we have to remove the bacteria, we filter. And as I was sort of saying, the thing that's really changed is we used to spend a lot of time working on all of the different phages, but now, as soon as we find them, we can go straight to sequencing their genomes. And this has really changed the way that we can do research, because straight away we have some information about what is encoding, the bacteriophage is encoding, what genes are they actually making, and how can we use this information. So I'm going to show you here some plots of, we call this phage clouds. So each little dot represents a phage genome. And the main thing I want you to see is, can you see when you see these big clusters of dots? They represent groups of related phages. And they have no relationship to any of the other big circles. So if you look at Salmonella, you can see there's about 20 circles. So there's no genetic at all affiliation. So you have very, very, very diverse phages affecting all of these different bacteria. So what I'd like you to see mainly is that there's different shapes, aren't there? The circles are different, connected in different ways. And this is giving you an idea of the biology of the phages. So what we now do is we zoom in. So for example, in Salmonella, the first cloud, all the yellow ones we have. So we can look at them, we can do many experiments and see, oh, actually, other ones, which group of phages are the most effective? Because phages didn't all evolve to kill all of their hosts, but we need to find the ones that are at a more aggressive end of the spectrum. So this is what we do. And then, when we've got phages that look like they're promising, we've understood their genomes, understand a bit more about how they work, we can then start to work out how we'll produce a useful product. And then there's also these logistical concerns. How do we regulate them? And also, how do we also potentially change them to give them alternative and better properties? So within the human context, we've spent a lot of time working on the gut, on the bladder, on the lungs, on the skin, because all of these areas are highly susceptible to bacterial infection. So we've been building up banks of all different types of bacteriophages that infect these organisms. Then, within animals, again, we've worked on many different types of animals. And then, within the sustainable food that I mentioned, we've been trying to find bacteriophages that will be able to target these very useful these bacteria that can degrade food. Because otherwise, we can spend a lot of time producing food, and then it rots, or it smells, and it's thrown away. So these are the main really promising areas for bacteriophage research. So I'm going to give you two quick examples now of how we might use phages in human health. The first is for urinary tract infections, because we know that there's 400 million cases of bladder infections diagnosed every year, resulting in about 250 million deaths. So we wanted to see, we have good phages that can kill the relevant bacteria, so do they work? Do they work in mice? So we have a mouse model, we can infect mice, we can collect the urine from the mice, we give them a little treat when they urinate, and we can collect the urine, we can look for phages, we can look for bacteria, and then we can count these. And actually, what's really was really sort of pleasing when we finally got to this point with our experiments was we could see, can you see that after one dose of bacteriophages within the bladder of the mouse, that infection, which is the blue bar, is completely gone. So we're able to remove the bacteria from the mice. So this is good news for the translation into humans. And also we can see in this graph, the green bar is showing us that there are more phages present when the bacteria are there. So they are replicating. So it's unlike any other form of medicine, because you have a self-replicating medicine at that site of infection. So the other example I want to quickly show you is using bacteriophages to remove salmonella. So salmonella, again, there's up to 1 billion cases of salmonella worldwide every year, resulting about 150 million deaths. It's carried by poultry, but the poultry don't actually get sick. But we want to see if we can decontaminate the poultry. So these are the experiments again. We infect the poultry, we collect the feces from the poultry after we infect them with phages, and we count the bacteria and phage. I'm just going to show you one graph from many, many large-scale trials of thousands and thousands of birds. But what you can see, if you just look, this is different concentrations of phages. Red is the control, blue, green, and yellow are increasing dosages of phages. And I just want you to see that if we give phages at the end of the last week of the life of the birds, can you see we've managed to eliminate the salmonella very clearly? There's none, nada, no salmonella left. So again, it's a really nice example where we could use phages to support sustainable agriculture and actually remove those pathogens from there to stop that build-up of resistant bacteria in the first place. So one of the reasons we're here at Futuro, Congreso Futuro is we're interacting with politicians, policymakers. So it's very important then to take this research, take this knowledge, and work with our hierarchy. This was me last year. I gave evidence in a UK inquiry. Actually, this morning, remotely, I gave evidence in another one. And so we're really working with the government to try and work out how to best position this technology. And in this phage cloud, you can see all of the different types of people we also have to interact with to make this happen. So, just to very much conclude my talk, I want to show you that hopefully I've convinced you that it's a very exciting time to be studying bacteriophages. There's lots of experiments to do now to help the future, lots of exciting opportunities for young scientists as well. And I think they should be useful both in food and health. So it just remains for me to very quickly thank all the people in my research team who help and produce the data that I've shared with you today. So thank you very much for your attention.